Now I want to talk about escape velocity. Escape velocity is the speed or velocity that you need to escape from the gravitational pull of a planet and to go out to infinity and not be bound to the gravity of the planet anymore. So how do we calculate the escape velocity of a planet or a moon or anything else? So I'm first going to assume that the object that's trying to escape is not going at any speed or rotating with the planet at all. So assume that the object is stationary here, like let's say a rocket, and just wants to escape. So what we do is we say kinetic energy initial plus the potential energy initial is equal to kinetic energy final plus potential energy final. When it goes out to infinity, the potential energy final is 0. And we're going to assume that the final kinetic energy, by the time that it escapes, it has barely, almost no kinetic energy, so it's barely escaped. So the final kinetic energy is also 0. So we have half mv initial squared. If you watch my lecture notes on the chapter on gravity, which is chapter 13 of the book, you'll see that I go through the derivation of the formula for the potential energy of a planet. You see that it's equal to negative g mass of the planet times mass of the object divided by distance d, and that's equal to 0 because the kinetic energy final and potential energy final is 0. So this is the potential energy of any object that is near or bounded to a planet. The big M is the mass of the planet, the little m is the mass of the rocket, and the little m cancel, and V initial is equal to the negative goes over to the other side, becomes positive, so you have square root of, and then the 2 multiplies divided by distance. Now, since you're near the surface, we're going to assume that the distance between you and the center of the planet is equal to the radius of the planet itself. So this distance here would be the distance from your center to the center of the planet. But since the rocket itself is pretty small, the distance between the rocket center and the planet center is almost equal to the radius of the planet. So we can change this to radius of the Earth, or we could call it radius of any other planet, and then we're going to call this velocity of escape. Okay, so let's calculate what the escape velocity from the Earth is. 2, and then the value of the gravitational constant. When you calculate all of this, this cancels this, makes it 10 to the 18. 10 to the 18 cancels that, makes that a 10 to the 7th. And then you can keep one of the 10s inside the radical, and then 10 to the 6th square rooted is a 10 to the 3rd. And then what's left is we could do 2 times 6.67259 times 5.974 times 10 divided by 6.378. We get 124. So the stuff under the radical is about 124. Square rooted that, 11.18. So the escape velocity comes out to be 11.18. 10 to the 3rd is same as a kilometer. So you're going to have kilometers per second. That's how fast a rocket has to go, a stationary rocket has to go in order to escape from the Earth's surface. That's called the escape velocity of the Earth. We could do likewise calculate the escape velocity from the Moon, from other planets. Jupiter is going to have a very strong escape velocity. The Sun is going to have a very, very strong escape velocity. Now, if you take into account the fact that if the rocket is at the equator of the Earth, the rocket is also spinning around, so it's going to have some velocity due to its spin, the rotation of the Earth. If the rocket is at the North Pole or South Pole, it's not going to have any tangential velocity. So this velocity would hold true at the North Pole and South Pole. At the equator, you're going to have some initial velocity due to your rotation. So it ends up, if we calculate the rotational velocity of the Earth, velocity of rotation is 2 pi times the radius of the Earth divided by the period t. So V of rotation, 2 pi times 6.378 times 10 to the 6th divided by the Earth rotates once in every 23.93 hours. On a later video, I'll talk about the rotational velocity of the Earth and the difference between sidereal day and the solar day. So I'll mention that and I'll go through the proofs of that. So the period T is 23.9344721138 hours. And then this one will give you the answer in meters. So then you're going to change this. 1 hour is 3,600 seconds. And then you're going to end up getting 465.09 meters per second. So the velocity of rotation at the equator of the Earth is that much. In kilometers per second, that gives you 0.465 kilometers per second. So it's about a half a kilometer per second. Is that going to help you out? Yeah, because you're going to have an initial tangential velocity. So your overall velocity needs to be 11.18. So if you're at the surface and you already have a tangential velocity of 0.465, okay, and you want to fly off, what your velocity should be here? Velocity perpendicular. The sum of the two is going to be 11.18 kilometers per second. So it's going to help you out kind of, but not too much, okay? You're going to end up getting still a necessary velocity of escape is going to be close to 11.18. So you could say this one is going to be 11.18 squared minus 0.465 squared to the power of 0.5. So it's going to be 11.17 kilometers per second. So did the rotation of the Earth help out the rocket much? Not really. You still need to go 11.17 kilometers per second in the perpendicular direction to escape from the Earth's gravity. This speed, by the way, kilometers per second, if we change that to the one that we know more, the miles per hour units, it comes out to equal 3,600 seconds is 1 hour. This one will give us the answer in miles per hour. 155 miles per hour. That's how fast the rocket has to go in miles per hour. That's very, very fast. Now, what happens if you have a satellite that's already a natural satellite of the Earth? Let's say we send it out to a certain height and it already became a satellite, okay? And now if that satellite, we want to give it extra speed so that it wants to escape. So that imagine as if the Earth is here, the satellite is here and it's rotating around the Earth. It could be here, rotating around the Earth this way. It could be here, rotating around the Earth this way. Let's assume that the height of the satellite from the Earth's surface is negligible, just for now. So if that natural satellite is orbiting around at a velocity necessary for it to keep orbiting around the Earth, so what is its escape velocity? So now, in your energy equation, kinetic energy initial plus potential energy initial, kinetic final plus potential final. Kinetic energy initial, it already has kinetic energy due to the fact that it is going around the Earth, okay, so it's a natural satellite. The potential final is still 0, kinetic final is 0, so you have half mv squared, v initial squared, plus half mv, because it's going around the circle, it has v perpendicular squared, right? It's going around, it's a centripetal velocity, minus gmm over r is equal to 0. Okay.